Hello, welcome to another lecture on mathematics for machine learning. Today we will learn what it means for a symmetric matrix to be positive definite or positive semi-definite. We call a matrix positive semi-definite if for any x element Rn, the squared form x transpose Ax is larger or equal to 0 for any arbitrary x. A different way to write positive semi-definiteness is that we use this roundish larger or equal sign to denote A larger or equal to 0. And this exactly means that A is positive semi-definite. Similarly to positive semi-definite, we define a symmetric matrix A to be positive definite if for all x element Rn that are unequal to 0, the squared form x transpose Ax is larger than 0. And similarly to the sign before, we introduced this roundish larger sign. So A larger than 0 indicates that A is positive definite. Note that positive definite is strictly stronger than positive semi-definite. So all positive definite matrices are positive semi-definite, but not the other way around. We can relate positive definiteness of a matrix to the eigenvalues of that matrix in the following way. A symmetric matrix is positive semi-definite if and only if all of its eigenvalues are non-negative. They are larger or equal to 0. And we would call a matrix positive definite, again, if and only if all of its eigenvalues are positive, so larger than 0. We can prove this very quickly by starting out with the matrix A, and we assume that it is positive semi-definite. So remember, it's an if and only if statement, so we have to prove both directions. So if the matrix A is positive semi-definite, then all of its eigenvalues are non-negative. And then we will have to prove the other way around, that if all of its eigenvalues are non-negative, the matrix also has to be positive semi-definite. So let's start with the one direction. So we assume that A is positive semi-definite, and we have to show that all of these eigenvalues are larger or equal to 0. Now let x, in this case, be an eigenvector of the matrix. Then 0 is smaller or equal to x transpose Ax. So this is using the positive semi-definiteness property of the matrix. And if we now multiply x by A, we get lambda times x, the eigenvalue times x. Now if we pull out lambda, then we get lambda times the inner product of x with itself. And from that we know that it is the squared of the L2 norm of x. Now lambda times the inner product of itself is equal to lambda times the squared L2 norm of x. And because the L2 norm is larger or equal to 0 for any x, and strictly larger than 0 for any non-zero x, and because we know that x is non-zero, because x is an eigenvector of A, the L2 norm is larger than 0. And because this term is larger than 0, the eigenvalue that we multiply this L2 norm with has to be larger or equal to 0. Because if we plugged in a negative number here, this inequality would be violated. So if we divide both sides by x, we have exactly the statement, namely that lambda is larger or equal to 0. Now for positive definite matrices A, the first step would be a strict inequality, and therefore also the last step, once we divide by the squared norm of x, would be a strict inequality, proving this direction. If A is positive definite, then all the lambdas are positive in the one direction. So in order to prove the second direction, we will use the Rayleigh quotients that we introduced in the last lecture. So if A is symmetric and all of its eigenvalues are non-negative, remember this is the assumption in the other direction. Now from this we have to prove that it follows that A is positive semi-definite. But then we know that for any x that is different from 0, the smallest eigenvalue is also larger or equal to 0. If you remember, the Rayleigh quotient is bounded below by the smallest eigenvalue and above by the largest eigenvalue. But here, we know that the smallest eigenvalue is larger or equal to 0 because all the eigenvalues are non-negative. Then, of course, the Rayleigh quotient also is larger or equal to 0. And we know that the Rayleigh quotient is defined as and because x transpose x is always larger than 0 for non-zero x, x transpose ax also has to be larger or equal to 0, because if we now divide by x transpose x by a positive number, we get x transpose ax is larger or equal to 0. And x transpose ax being larger or equal to 0 for any non-zero x is exactly the definition of positive semi-definiteness. In fact, if x equals 0, this would also be exactly 0. Now, if we assume that the eigenvalues of A are all strictly positive, then again this becomes a strict inequality. So we know lambda min is larger than 0 and A is positive definite. So why are positive definite matrices so important? Well, the way we typically get positive definite matrices is by taking an arbitrary matrix A and multiplying it by its transpose. So if A is an m by n matrix, then A transpose A is positive semi-definite, as is A transpose, by the way. And if the only solution to Ax equals 0 is 0, so if it follows that x equals 0 from Ax equals 0, then so the null space of A is exactly the set of including the 0 vector, then it is positive definite. So what does this mean? This means that null of A is the set of all x with x equals 0. So let's prove this proposition. So for any x, you have to show that x transpose times A transpose AX is larger or equal to 0. So if we pull in A in front of x, we get the inner product between AX and itself, which is equal to the squared L2 norm of AX, which is larger or equal to 0. Because AX is again some vector, and for any vector, the squared L2 norm is larger or equal to 0. And this proves the positive semi-definiteness case of A transpose A. If the squared L2 norm of a vector AX is 0, then also the L2 norm of AX is 0. The L2 norm is 0 only for the 0 vector, which implies that this term is 0 only if AX is 0. Thus, if for any non-zero x, AX is different from 0, because the null space is only the set containing the 0 vector, we know that A transpose A must be positive definite. Because, remember, positive definite, the definition is that for any non-zero x, the squared form in the matrix is larger than 0. So if the null space is the set containing only the 0 vector, then AX equals 0 implies that x equals 0, because this is the only solution to this equation here. Thus, the squared form x transpose A x equals 0 if and only if x equals 0, which means that A transpose A is positive definite. Now, because all the eigenvalues of a positive definite matrix are larger than 0, we also know that this matrix is invertible. Remember, one way to create the inverse of a matrix is by starting out with the spectral decomposition of this matrix, so the matrix of the orthogonal eigenvectors times the inverse of the eigenvalues, so 1 divided by the eigenvalue, which is of course only computable if they are non-zero, which they are for a positive definite matrix, times the eigenvector matrix transpose. Thus, if all the eigenvalues are larger than 0, this is computable and the matrix A is invertible. Now, if the matrix is positive semi-definite, then it may be that some of the eigenvalues are exactly equal to 0. In this case, the matrix would not be invertible. However, because all the other eigenvalues are larger than 0, so none are negative, we know that if we add a small constant to the diagonal of this matrix will be positive definite, and that we can show in the following. Because if A is positive semi-definite and we have a small positive constant, then the squared form of x transpose times A plus this matrix that has epsilon added to the diagonal times x equals, well, the squared form in A plus the squared form in the identity times epsilon. The second term is nothing different than the inner product of x with itself, so it's the squared L2 norm times epsilon. Now this, because x is different from 0, is a positive number, and this squared form in this positive semi-definite matrix is larger or equal to 0, so it's non-zero. And the sum of a non-zero and a positive number needs to be positive. Thus, this matrix A plus E times I is positive definite if A is positive semi-definite. And the sum of that is the norm of AX squared, which is larger or equal to 0, because if AX is 0, so if X is an element of the null space of A, then this can be 0. Otherwise, it will be a non-zero vector that we're taking the norm of, so this will be larger than 0. So the norm squared of AX is larger or equal to 0, plus the norm of a non-zero vector obviously is larger than 0, times epsilon, which is a small positive constant. So we are again adding a non-negative constant to a positive constant. We get a positive constant. In machine learning, you will often see that quadratic forms are visualized using ellipses that correspond to level sets of this quadratic form. Now, the level set or isocontour of any function, such as a quadratic form, is the set of all inputs where the function yields exactly the same value. So, mathematically, the C isocontour of f is the set of inputs x of this function from the domain of f, where if you plug x into f, you get c back. Let's consider the special case where f is the squared form in a positive definite matrix A. Because A is positive definite, we can actually take its square root. So remember, we can take arbitrary powers using the spectral decomposition by taking powers of the eigenvalues. So A to the 1/2, so the square root of A, is q times lambda to the power of 1/2, lambda the eigenvalues and q the matrix of orthogonal eigenvectors, times q transpose. In this case, A to the power of 1/2, so the square root of A, has to be positive definite, as can be seen, because if all the eigenvalues of A were positive in the first place and we're taking the square root of them, the square root of any positive number is still a positive number. Thus, the eigenvalues of A to the power of 1/2 will also be positive. Now let's also fix some value c that is larger or equal to 0. In this case, the C isocontour of this squared form of f is the set of x from Rn, where C equals x transpose AX, which is equal to, well, the square root times the square root. Remember, if we multiply times q lambda 1/2 q transpose, so this is a 1/2, because q is an orthogonal matrix, this becomes the identity. Lambda times 1/2 times lambda 1/2 becomes lambda. We get just A. So this equals Q lambda Q transpose. So we can write this squared form in using a to the power of 1/2 times a to the power of 1/2, which means that we can pull a to the power of 1/2 into x. And then we have again an inner product of some vector, that is the product of this a to the power of 1/2 times x with itself. So if this vector is non-zero, this has to be non-negative, as it is the squared L2 norm. Now we know that because a to the power of 1/2 is positive definite, if a is positive definite, that a to the power of 1/2 times x is always a non-zero vector unless x itself is 0. Thus, this term is larger than 0, which means that x transpose ax is 0. Now that we have established that this squared form x transpose ax is equal to the squared norm of a to the 1/2, so the square root of a times x, we can make a change of variable and introduce z equals a to the 1/2 times x. We additionally have this condition, because we're interested in the level set of this function, that the L2 norm of z, so of a to the 1/2 of x, is the square root of c. Remember, x transpose ax equals c. That's what we're interested in, the set of x for which this function, this squared form, equals c. Thus, the square root of this needs to be square root of c. And the L2 norm of z is the square root of our initial squared form. So because we're talking here about the norm of a vector z that has to be equal to square root of c, we are actually defining this level set as a sphere with radius square root of c. We can again reparameterize that using some c hat times the square root of c, where c hat is a vector that has unit norm. Then, since the inverse of the square root of the matrix A, so a to the power of minus 1/2 equals, again using the spectral decomposition and taking powers of lambda, this equals q times lambda to the minus 1/2 times q transpose. We can, from c, get x back. So x equals a to the power of minus 1/2 times c, so it's the square root of the inverse of a times z. This equals to, well, q times lambda to the minus 1/2 q transpose times c hat times square root of z, which we can again replace by some vector c tilde that we get by multiplying c hat by q transpose, which has exactly the same norm as c hat. So c tilde still has norm 1 because q transpose is an orthogonal matrix, which means that if we multiply a vector, we're only rotating this vector, but we're not changing the length of this vector. So it still has unit norm. Under this parameterization, we see that this level set, so the set of all x from Rn, where this function, which is the squared form in A, equals to a point C. So this set is exactly, as we have just shown, the image of the unit sphere, which is the set of these z tilde element Rn that have unit norm, where x is obtained using the invertible linear map square root c times q times lambda to the minus 1/2 times this unit norm vector z tilde. So this means we are first starting out with the unit sphere. So these are our z tilde. So the circle is the set of all of these unit norm vectors. Then we are multiplying this by some matrix lambda to the minus 1/2. Remember, lambda to the minus 1/2 is a diagonal matrix that only has positive diagonal entries. So what that means is that we're taking all these directions and we're multiplying them by some positive number, which may be larger than 1 or smaller than 1. The result of this lambda to the minus 1/2 times z tilde will be some axis-aligned ellipse. So this is times lambda minus 1/2. And if we now multiply this by q, we are rotating it. So then it becomes non-axis aligned. So this would be q times lambda minus 1/2 times z tilde. We're still having corresponding to z's that have unit norm. So far we have squeezed our coordinate axes, then rotated, because Q is an orthogonal matrix. If we multiply a vector by an orthogonal matrix, we're rotating it, but not changing its norm. And then we are multiplying by the square root of c. So then c is larger than 1, then we get some larger ellipse back. And if it's smaller than 1, we get a smaller ellipse back. So let's c times q times lambda to the minus 1/2 times z tilde, or x. So this is the set of all x in Rn, where the squared form in A, this positive definite matrix A, equals C. So again, to repeat, what we've gained from all of these manipulations is some algebraic understanding of the C isocontour of F, our squared form, in terms of a sequence of linear transformations applied to the unit sphere, which is a quite well understood set. So first, we have the unit sphere, then we scale the axes of this unit sphere with lambda to the power of minus 1/2, resulting again in axis-aligned ellipsoids. Then we are rotating this, and then we multiply that by the square root of c. Now observe that the length of these ellipsoids are proportional to the inverse of the square root of the eigenvalues of A. That means that for dimensions where we have large eigenvalues, we actually will get tighter, and if we have small eigenvalues, then it will be going far. So to summarize, we looked at positive semidefinite matrices. So a matrix is positive semidefinite if any squared form x transpose AX is non-negative, which is equivalent to all the eigenvalues being non-negative. This is more general than saying that the matrix A is positive definite. So Every positive definite matrix is positive semi-definite as well, which means that for any non-zero x, x transpose ax, the squared form is positive, which is equivalent to saying that all the eigenvalues are positive. Then the level set or isocontours of the squared forms in positive definite matrices are ellipsoids, where the axes point in the directions of the eigenvalues, Qi, of this matrix, and the radii of these ellipsoids, of these axes, are proportional to the inverse of the square roots of these eigenvalues, lambda I. And with this, I want to say thank you and goodbye, and see you in the next video. Bye bye.